A man steps into a time machine and prevents his own birth. This is the grandfather paradox, a puzzle that reveals time travel is more than science fiction. We are about to journey through 30 distinct theories that attempt to crack this cosmic code, from Einstein's relativity to the edges of quantum mechanics. You will gain a clear understanding of how time travel could theoretically work, stripping away the Hollywood glamour for genuine scientific speculation. We will explore how a spinning universe might let you meet your past self, and whether physics itself has a built-in paradox prevention system. If you could send one message to your past, what would it be? Einstein shattered our intuitive sense of a universal clock with his theory of special relativity. He proposed that the faster you move through space, the slower time passes for you relative to someone standing still. This is not a mechanical error or an illusion, but a fundamental warp in the fabric of reality itself. Consider the famous twin paradox. One twin boards a spaceship and journeys to a distant star at a speed approaching light, while the other remains safely on Earth. Upon the traveler's return, only a few years might have passed for them, but they step back onto a world where decades have flown by. The Earth-bound twin is now old and gray, while the astronaut remains scarcely aged. This is time dilation in action, a proven phenomenon that affects everything, even the precise atomic clocks on orbiting satellites, which must be constantly corrected. Time is not a river flowing at the same rate for everyone. It is more like a personal rhythm, a beat that changes its tempo based on your motion. Visualize two identical clocks, one sitting on a desk and the other racing around the Earth in a jet. When the traveling clock returns, it will show a slightly earlier time than the one that stayed put. This is the very essence of time travel into the future, a one-way journey available to anyone who moves fast enough. So, if time is this malleable, what other keys might unlock its deepest secrets? But Einstein did not stop with motion. His theory of general relativity took this strange reality a step further, proposing that gravity itself is not a force pulling on things, but a warp in the very fabric of spacetime. Picture a taut rubber sheet representing the cosmos. When you place a heavy object like a planet in the center, it creates a deep dip. A smaller marble rolling nearby will curve into that dip, not because of a mysterious tug, but because it is following the curved path of the sheet itself. This is gravity, and just as that rubber sheet is stretched taut around the heavy object, time is also stretched. The stronger the gravity, the more time slows down. This is gravitational time dilation. We see this not just in thought experiments, but in our everyday technology. The Global Positioning System, or GPS, relies on a network of satellites orbiting high above Earth, where our planet's gravitational grip is slightly weaker. The clocks on these satellites actually run faster than identical clocks on the ground. If engineers did not constantly correct for this tiny difference, your phone's navigation would be off by several miles within a single day. Now take this concept to its extreme. Imagine approaching a black hole, an object with gravity so intense that not even light can escape. If you could hover just at its edge, time for you would slow to an incredible crawl relative to the rest of the universe. From an outside observer's perspective, your movements would appear to stretch out into frozen, slow motion. You might experience just a few minutes, while centuries, even millennia, could pass for everyone else. This is another form of one-way travel into the distant future, a journey powered not by speed but by gravity's immense weight. So if gravity can bend time, what other cosmic structures might twist it into a loop? If gravity can bend the fabric of the cosmos, could it also stitch it together? This brings us to the third theory, wormholes, the universe's potential secret passages. An Einstein-Rosen bridge, the formal name for a wormhole, is a theoretical tunnel through the very substrate of spacetime. Picture the universe not as a flat sheet, but as a vast folded piece of paper. A wormhole would be a tiny tube connecting two distant folds, creating a shortcut that bypasses the long journey across the surface. A traveler entering one mouth could, in theory, emerge from the other almost instantly, having crossed a distance that would take light millions of years. Yet the possibility becomes even more profound when we consider time. If one end of the wormhole were moved, perhaps by taking it on a high-speed journey, time dilation would cause the clocks at each mouth to fall out of sync. Entering through the stationary end might lead you to exit the moving end in its relative past or future, making the tunnel a conduit not just for space but for time itself. However, building and using such a gateway faces almost insurmountable hurdles. The primary challenge is stability. According to our current understanding, the gravitational forces at the wormhole's throat, its narrowest point, would be so immense that the tunnel would pinch shut instantly, crushing anything inside. The only way to prop it open, theorists suggest, is with a substance known as exotic matter. This is not just rare or unknown material, but something that possesses negative energy density, effectively generating a kind of anti-gravity that pushes the walls of the wormhole apart. While tiny amounts of negative energy might be possible in quantum mechanics, creating the vast quantities needed to stabilize a human-sized passage remains firmly in the realm of speculation. So if a stable tunnel is so difficult to create, could the universe already provide its own ready-made time machines? The universe might already contain its own ready-made time machines, woven into the fabric of reality from the very first moments of creation. These are cosmic strings, hypothetical relics from the universe's explosive birth. Think of them not as physical strings you could touch, but as unimaginably dense flaws in space-time itself, thinner than a single atom but stretching across the entire cosmos. Each one would contain the mass of an entire galaxy compressed into an infinitely long, one-dimensional thread. Their gravitational influence is so profound that they could literally bend the universe around them. Now, imagine two of these cosmic filaments moving past one another at a significant fraction of the speed of light. The combined gravitational warping of these two ultra-dense lines could twist the fabric of spacetime into a loop known as a closed time-like curve. This is the technical term for a path that would allow a traveler to journey back to their own starting point in both space and time. It would be like drawing a circle on a map that not only brings you back to your hometown, but also to the exact moment you first left. You would not need a machine, only a spacecraft capable of navigating this predetermined cosmic racetrack. The very idea springs from our most advanced models of cosmology, theories that describe the universe's conditions in the first fleeting instants after the Big Bang. Yet, for all its theoretical elegance, the cosmic string time machine remains profoundly speculative. No direct evidence for these cosmic strands has ever been found, and their existence is still a matter of intense debate among physicists. Even if they do exist, finding two perfectly aligned and moving at the required relativistic speeds presents a challenge of astronomical proportions. This theory pushes the limits of our imagination, suggesting that the blueprints for time travel might be written into the oldest structures of the cosmos, waiting to be discovered. If such primordial threads are real, what other impossible journeys might they make possible? Another theoretical machine bends the rules of time not with strings but with spin. Physicist Frank Tipler proposed a cylinder of almost unimaginable proportions. This would not be a simple metal pipe, but an object infinitely long and made of a material so incredibly dense that its gravity alone would warp the space around it. The true magic, however, happens when this colossal cylinder begins to rotate, spinning at a significant fraction of the speed of light. It is this furious motion that performs the real trick, dragging the very fabric of spacetime along with it, like a spoon stirring a thick cosmic fluid. As spacetime is twisted into a whirlpool around the cylinder, it could theoretically fold into a path called a closed time-like curve. A spacecraft following this specific spiraling path around the spinning cylinder would not just travel in space, it would find itself on a trajectory that loops back to its own past. You could fly in a precise orbit and return to your starting point before you ever left. The engineering required for such a device is, to put it mildly, beyond our current reach. The cylinder would need to be infinitely long to function as predicted, a requirement that is physically impossible in our finite universe. Furthermore, the immense forces involved would likely tear any known material apart, perhaps requiring exotic matter just to hold its shape. This places the Tipler cylinder firmly in the realm of mathematical elegance, a beautiful idea that demonstrates how rotation could twist time into a knot, even if we could never actually build one. Even a universe spinning in its entirety could become a time machine. The brilliant logician Kurt Gödel, a close friend of Einstein, discovered this startling possibility within the equations of general relativity itself. Gödel found a solution that described a cosmos where everything, all the galaxies and stars, were slowly rotating together. In this rotating universe, the fabric of space-time is dragged along by the motion, creating a subtle but pervasive whirlpool effect. If you were to embark on a long, looping voyage through such a cosmos, following a precise and incredibly vast path, you could eventually return to your starting point in space, but also to a moment before you ever left. You would not be moving faster than light or diving into a black hole. You would simply be riding the natural, twisted geometry of a spinning reality. This closed time-like curve is a direct consequence of the universe's overall rotation, a built-in path to the past. Yet, for all its mathematical elegance, we are fairly certain we do not live in a Gödel universe. Our extensive observations of the cosmos show no evidence for such a universal spin. The distribution of galaxies and the faint afterglow of the Big Bang, the cosmic microwave background, appear uniform and isotropic, showing no preferred axis of rotation that Gödel's model requires. So why does this theory remain so important? It stands as a profound proof of principle. It demonstrates, using Einstein's own equations, that the laws of physics do not inherently forbid travel into the past. The barrier is not a rule written in cosmic law, but rather the specific, accidental conditions of our own, apparently non-rotating universe. Gödel showed us that time travel is not a fantasy to be dismissed, but a latent potential within the very geometry of spacetime, waiting for the right conditions to be unlocked. If the entire universe could theoretically permit such journeys, then perhaps the key lies not in the whole cosmos, but in the bizarre rules that govern its smallest parts. Perhaps the ultimate safeguard against paradox is not a law of physics, but a law of consequence. The Novikov self-consistency principle proposes a universe that is fundamentally logical, a single, unchangeable timeline where the past is just as fixed as the present. This idea, developed by Russian physicist Igor Novikov, asserts that if time travel were possible, any actions taken by a traveler would have already happened. You could journey to the past, but you would find yourself powerless to alter it in any meaningful way. Your presence there was always a part of the historical record, and your actions would inevitably conspire to maintain the timeline's consistency. Think of the grandfather paradox once more. A traveler goes back with the intent to prevent their grandfather from meeting their grandmother. Under Novikov's principle, this act is simply impossible. The gun would jam, a sudden distraction would occur, the traveler would have a last-minute change of heart. Some sequence of events, whether mundane or miraculous, would always intervene to ensure the meeting happens exactly as it always did. You are not an author rewriting a book, but a character who was always present in the story, your actions already woven into the narrative's fabric. This principle favors a deterministic universe, one where free will for the time traveler is an illusion. Every choice you make in the past was predetermined to lead to the present you just left. It is a cosmic version of a perfect, self-healing script. While this neatly sidesteps the logical nightmare of paradoxes, it raises a profound question about our own agency. Are we truly making choices, or are we merely acting out a story that has already been written, with time travelers playing their pre-assigned roles from the very beginning? If the timeline is truly this rigid, then what happens when we introduce the infinite possibilities of the quantum world? The rigid logic of Novikov's principle presents a universe with a single, unchangeable story. But what if our story is not the only one being told? The many worlds interpretation of quantum mechanics offers a breathtakingly different solution to the paradox of time travel. This theory suggests that every single quantum event, every tiny decision, does not just have one outcome but all possible outcomes. Each one plays out in its own newly created, fully real universe. Think of reality not as a single road but as an endlessly branching tree. At every fork, the universe splits. In one branch, a radioactive atom decays at this very moment. In another, it does not. In one world, you turned left on your way home. In another, you turned right. Every possibility is realized somewhere. Now, place a time traveler into this cosmic landscape. They build a machine and journey into the past. According to the many worlds view, they are not traveling back into their own past. Instead, the moment they arrive in a previous era, they step into a new, parallel branch of reality. Their original timeline remains completely untouched and safe. This means the grandfather paradox simply evaporates. If you go back and prevent your grandparents from meeting, you are not creating a logical contradiction. You are merely activating a new branch of the multiverse where you were never born. Your own history in your home universe remains perfectly intact. You can walk through the past, change a major historical event, or leave a message for your younger self, all without fear of erasing your own existence. Your actions do not rewrite history, they write a new one in a new volume on an infinite shelf. This theory transforms time travel from an act of dangerous editing into one of boundless exploration. You could visit any point in the past, but you could never return to the exact future you left, because that timeline is now just one of an infinite number of parallel worlds. The many worlds interpretation offers a universe of infinite second chances, where every possible past and every potential future is real. If every choice creates a new world, what does that say about the path you are on right now? These looping paths through reality are known as closed time-like curves. The name itself describes their function. A time-like curve is simply the path an object follows through the four-dimensional fabric of space-time. In our normal experience, these paths always move forward in time, never looking back. But a closed time-like curve is a path that bends in such a way that it loops back to reconnect with its own past. It is a cosmic racetrack where the finish line is also the starting gate, and completing the lap means you arrive before the race even began. These are not science fiction inventions, but legitimate, if exotic, mathematical solutions that emerge directly from Einstein's theory of general relativity. They appear in the equations that describe the space around a massively rotating black hole, a Kerr black hole, or in the theoretical framework of certain stable wormholes. In these extreme environments, the fabric of spacetime is so twisted by immense gravity and spin that the forward arrow of time is bent into a circle. An astronaut traveling along such a curve could, in principle, embark on a journey and eventually find themselves back at the exact same location and moment from which they departed, creating the potential to meet their own past self or witness historical events firsthand. This possibility strikes at the very heart of causality, the fundamental principle that cause must always precede effect. A closed time-like curve shatters this logical sequence. It allows for an effect, the returning time traveler, to exist before its own cause, the moment they began their journey. This creates the potential for paradoxes that seem to defy all rational explanation. Could you hand yourself the plans for the time machine before you even invented it? Could a message you receive in the past be the very one you send in the future? Physicists are deeply divided on whether nature actually permits these loops. Some, like Stephen Hawking, propose the chronology protection conjecture, a hypothetical cosmic censorship that would prevent closed time-like curves from forming, perhaps through some yet undiscovered quantum gravitational effect that makes such paths unstable. Others argue the mathematics is clear, and if the universe allows for the conditions, however extreme, then the loops are possible. The debate is far from settled, forcing us to question whether the flow of time is a fundamental law of the cosmos, or merely a local condition we experience in our quiet corner of a much stranger universe. If such loops are possible, even in theory, what does that say about the nature of our own past? Is it truly set in stone, or could it be a place we might one day visit? While closed time-like curves bend time into a loop, another theory suggests a more direct path to the past, one that moves faster than the cosmic speed limit itself. Tachyons are purely hypothetical particles that, by their very definition, always travel faster than light. According to the strange logic of special relativity, as an object approaches the speed of light, its mass becomes infinite and time for it slows to a halt. Tachyons, born on the other side of that barrier, would operate under an inverted set of rules. For a tachyon, traveling faster than light would be its normal state of rest. Its energy would decrease as it accelerated, and most strikingly, from our slower-than-light perspective, it would appear to move backwards in time. A message encoded using tachyons could be received before it was ever sent, creating a direct line to the past. This potential for backward time travel is precisely why most physicists view tachyons with deep skepticism. Their existence would shatter the principle of causality, the bedrock of all science, which states that cause must always come before effect. If you could receive a tachyon message warning you of a disaster, then prevent that disaster, what caused the message to be sent in the first place? This creates an instant, unresolvable paradox. Despite decades of searching, no experiment has ever detected a tachyon or any sign of faster-than-light information transfer. They remain a fascinating mathematical quirk in certain equations, a ghost in the machine of particle physics, more a staple of science fiction than established science. They represent a universe where time's arrow is not fixed, but for now, that universe remains locked in the realm of elegant equations and profound questions. If a particle could truly dance backwards through time, what symphony of cause and effect would it leave in its wake? The spooky connection between entangled particles might whisper secrets about time itself. In the quantum realm, two particles can become linked or entangled in such a way that measuring the state of one instantly determines the state of the other, even if they are light years apart. This instantaneous connection, which Einstein famously called spooky action at a distance, seems to defy our everyday understanding of space, but some theorists push this strangeness even further into the domain of time. They propose a radical idea known as retrocausality. In this speculative view, the act of measuring a particle today could, in some sense, reach back and influence its entangled partner in the past. It is as if the decision you make now sends a ripple backward through time, setting up the conditions that made your decision possible in the first place. Imagine two coins, each sealed in a box and sent to opposite ends of the earth. You open your box and see the coin is showing heads. At that exact instant, you know with certainty that the other coin is showing tails. In a standard quantum view, the outcome was always set, just unknown. But in a retrocausal interpretation, your act of looking might be what forced the distant coin and its entire history leading up to that moment to become tails. This is not time travel in the classic sense of a person stepping into a machine, but a potential form of backward time causation at the most fundamental level of reality. Could the present be quietly shaping the past? Mainstream physics largely rejects this idea, upholding the standard view that the particle states were correlated from the moment they became entangled, with no mysterious backward influence. The mathematics of quantum mechanics works perfectly well without needing to invoke retrocausality. Yet this controversial theory persists at the fringes, a tantalizing hint that our arrow of time may not be a one-way street after all, but a two-way conversation between what is and what was. If particles can indeed whisper across time, what other conversations might be happening just beyond our perception? Miguel Alcubierre offered a stunning escape from the cosmic speed limit, not by breaking the rules but by rewriting the road. His warp drive concept cleverly sidesteps the prohibition on faster-than-light travel by moving the space around a ship rather than pushing the ship through space. Imagine a surfer riding a wave. The surfer themselves is not moving the water, they are carried forward by the wave's own motion. In the Alcubierre model, a spacecraft sits inside a stable pocket of spacetime, a warp bubble. The fabric of the universe in front of this bubble is violently compressed, while the spacetime behind it is dramatically expanded. The bubble and everything inside it is then simply swept along this artificial wave, potentially at speeds that dwarf that of light. Critically, the ship itself is motionless within this local pocket. Since it is not accelerating through space, it avoids the punishing relativistic effects that would normally prevent such velocity, and the travelers would feel no g-forces at all. This manipulation of spacetime itself creates a profound time dilation effect. For the crew inside the bubble, time would pass normally. They could embark on a journey that feels like a few weeks. But upon returning to normal space, they would find that centuries had flown by for the rest of the universe. They would have effectively traveled into the future, becoming relics of a bygone era. The energy required to create and sustain such a warp bubble, however, is almost incomprehensible. Initial calculations suggested you would need the equivalent of a planet's mass converted directly into energy. Later refinements hinted that a mass the size of a spacecraft might suffice, but this still represents an astronomical amount of power, far beyond anything our civilization can even conceive of generating. Furthermore, the drive would require exotic matter with negative energy density to stabilize the bubble and prevent it from collapsing, the same mysterious substance needed for traversable wormholes. While the Alcubierre drive remains a beautiful piece of theoretical physics, it highlights a recurring theme. The universe may allow for incredible journeys, but the price of admission is a key we have yet to forge. If bending space itself is the path to other stars and other times, what other cosmic materials might we one day learn to shape? We often speak of time as a river flowing in one direction, but what if that is merely a limitation of our own perception? The theory that time is a dimension proposes a far more static and complete reality. Just as we move freely through the three dimensions of space, forward and back, left and right, up and down, time may be a fourth dimension through which we are constantly traveling, but only in one fixed direction. This idea is crystallized in the block universe theory, a model where the past, present, and future are not successive states but permanent fixtures. Think of the entire history of the cosmos not as a story being written page by page, but as a finished book. Every event from the Big Bang to the last star burning out exists simultaneously within this block. Your birth, your life, and everything that will ever happen to you are already there, written into the fabric of this eternal now. In this view, time travel would not be about changing history, but simply about gaining the ability to move your awareness to different coordinates within the block. If you could step outside of your one-way journey, you could navigate to any chapter you wished, revisiting yesterday or observing 1,000 years from now. A powerful analogy is a movie on a DVD. All the scenes exist on the disc at once, complete and unchangeable. When you press play, your consciousness is like the laser in the DVD player, illuminating one frame after another in a predetermined sequence, creating the illusion of a flowing narrative. But the entire movie, from opening credits to final scene, is already present. If we could somehow learn to move that laser freely back and forth across the disc, we would experience time travel. This resolves the paradox of a changing past because in the block universe, the past is not altered. A time traveler going back was always a part of that past scene, their presence woven into the original recording. This is a universe of profound determinism, where free will might be the experience of reading the book without knowing the ending, even though the last page is already printed. The block universe suggests that our journey through time is not a creation but a discovery. So if all of time is already laid out, what does that say about the choices you believe you are making at this very moment? Stephen Hawking once proposed a powerful cosmic safeguard, a law of physics that actively defends the flow of time itself. He called it the chronology protection conjecture, a principle stating that the universe will always step in to prevent time travel to the past on any meaningful human scale. Hawking was deeply troubled by the paradoxes that closed time-like curves could create, and he famously quipped that the absence of tourists from the future is strong evidence that time travel is impossible. His conjecture suggests that nature has a kind of immune system, one that identifies and neutralizes any situation that could lead to a paradox before it ever forms. Imagine trying to create a stable wormhole time machine. Just as you are about to stabilize the throat with your exotic matter, an incredible buildup of energy would occur. Virtual particles, which constantly flicker in and out of existence at the quantum level, would be caught in a feedback loop. They would travel through the wormhole, re-emerge in their own past, and then travel through again, their energy compounding with each cycle. This radiation would swiftly amplify to an infinite intensity, creating a firewall of pure energy that would either destroy the wormhole instantly or render the entrance to the past completely impassable. The universe, in this view, does not simply forbid time travel with a written law. It enforces the rule with physical violence, deploying quantum effects or gravitational instabilities to obliterate the time machine at the moment of its creation. This is not a gentle suggestion from the cosmos, but a fundamental and violent rejection of any attempt to twist causality into a knot. It is as if reality itself has a profound allergy to paradox, and the chronology protection conjecture is its emergency response. If Hawking was right, then the timeline we experience is not just a happy accident, but a carefully protected sequence of cause and effect, shielded by the universe's own defensive mechanisms. But does this cosmic guardian leave any room for exceptions, or is the door to the past permanently sealed shut? Deep within the heart of a spinning black hole, the universe's rules unravel. A Kerr black hole, named for the physicist who discovered the solution, is not a static pit but a cosmic whirlpool of unimaginable power. Its intense rotation drags the fabric of space-time around with it, twisting reality into a vortex. While the outer event horizon marks the point of no return for light and matter, the true mystery lies deeper within. Theoretical models suggest that past this boundary, there could be a second inner horizon. It is here, in this violently warped inner sanctum, that the equations of general relativity predict the existence of closed time-like curves. These are not paths you would find on a map, but trajectories woven into the twisted geometry itself. A spacecraft, having somehow survived the journey to this point, could theoretically follow one of these loops and travel into its own past. You would not be steering a ship so much as riding a pre-existing current in the river of time, a current that flows in a circle. The potential for such a journey is written directly into Einstein's most trusted equations, suggesting that the most destructive objects in the cosmos might also be nature's most profound time machines. Yet reaching this theoretical gateway is a feat beyond any nightmare. The journey toward the event horizon alone is fraught with cosmic violence. As you approach, the difference in gravity between your head and your feet would become astronomical. You would be stretched into a long, thin stream of atoms, a process physicists call spaghettification. Any structure, no matter how robust, would be torn apart into a cascade of elementary particles long before it reached the inner chaos. Furthermore, the inner horizon itself might not be a serene gateway, but a wall of infinitely blue-shifted radiation, a firewall of accumulated energy from the entire future history of the universe focused into a single destructive plane. So while the mathematics offers a breathtaking possibility, the physical reality presents an almost certain death sentence. The black hole time machine is a ghost in the equations, a tantalizing potential that remains locked away behind forces that obliterate everything they touch. If the key to the past lies within such a destructive heart, could there be a safer way to access the timelines it might contain? Even the most humble substance in the cosmos, a simple cloud of dust, could theoretically become a gateway to yesterday. This is the promise of two obscure solutions to Einstein's equations, the Van Stockum dust and the Bonners rotating dust. Picture not a solid object, but a vast, swirling cloud of microscopic particles, all rotating in perfect unison around a central axis like a silent, cosmic whirlwind. According to general relativity, any form of mass or energy warps space-time, and rotation adds a crucial ingredient, an effect known as frame dragging. This is the same phenomenon that twists space-time around a spinning black hole, but here it is generated by the collective motion of countless tiny specks. In these highly specific and idealized models, if the dust cloud is infinitely long and rotates at just the right, incredible speed, the frame dragging becomes so powerful that it doesn't just twist space-time, it ties it into a knot. The fabric of reality is warped so severely that paths called closed time-like curves emerge within the cloud. A traveler could fly a spaceship on a precise spiral trajectory through this swirling dust and find themselves looping back to a point in their own past. The beauty of this theory lies in its simplicity. It requires no exotic matter or impossible materials, just ordinary dust set into a perfect, furious spin. Yet this simplicity is also its greatest limitation. These models are mathematical fantasies, relying on conditions that could never exist in our messy universe. The dust cloud must be infinite in length, a physical impossibility, and it must maintain an impossibly perfect, frictionless rotation without collapsing under its own gravity or clumping into stars. There are no known forces that could orchestrate such a delicate and vast cosmic ballet. So while Van Stockum and Bonners dust clouds stand as elegant proofs that even the most mundane matter could, in principle, unlock time travel, they remain captivating thought experiments, ghostly blueprints for machines made from starlight and silence. If a cloud of dust can hold such power, what other ordinary aspects of our universe might conceal extraordinary secrets? A melody echoes through time with no composer. This is the bootstrap paradox, a loop of existence with no clear beginning or end. Imagine a young composer struggling to find their voice, who one day receives a package from an anonymous sender. Inside are the complete sheet music for 9 breathtaking symphonies. They publish the work under their own name to instant and everlasting fame, celebrated as the greatest musical genius of their age. Years later, now old and renowned, they decide to ensure their own success. They copy the symphonies by hand, place them in a box, and use a time machine to deliver the package to their own despairing younger self. The music was never truly created. It simply always existed, trapped in an infinite loop where it is its own origin. Where did the symphonies originally come from? The question has no answer. The loop is perfectly self-contained, a closed circle of causality with no external cause. This paradox brutally challenges our most basic assumption that every effect must have a prior cause. Here, the effect is the cause, and the cause is the effect, locked in a dance of mutual creation. Some theories, like the Novikov self-consistency principle, could allow for such a loop. In that deterministic universe, the music always was and always will be passed back, a fixed part of a single, unchangeable timeline. The loop is not a flaw, it is simply how that piece of history always unfolded. Yet the many worlds interpretation offers a different escape. Perhaps the composer, upon receiving the music, creates a new branch of reality. In that new timeline, the music has an origin the moment it was received from another universe. The bootstrap paradox forces us to confront the nature of creation itself. Can something truly come from nothing if that nothing is its own future? A predestination paradox ensnares a time traveler in a cruel, self-fulfilling loop. Their very attempt to change history becomes the engine that drives it, locking events into a prison of their own making. Picture an agent sent to prevent a pivotal political assassination. They arrive in the past, navigate the crowded city square, and position themselves to intercept the fatal bullet. As the assassin takes aim, the agent lunges to push the target to safety. But in that moment of frantic action, they accidentally jostle a bystander who stumbles into the path of the target. The target, startled and knocked off balance, stumbles directly into the line of fire. The shot rings out. The agent's desperate effort to save a life was the precise series of actions that ensured the death occurred. They did not alter the timeline. They completed it. Their presence in the past was never an intervention, but a vital, hidden component of the historical record, a cog in a clockwork that was always meant to tick this way. This paradox presents a universe of profound determinism, where free will is a devastating illusion for the traveler. You believe you are making choices, but every decision you make has already been accounted for, woven into the fabric of a past that requires your participation to unfold correctly. The event you witness in your present was always caused by your future meddling in the past. This creates a loop with no beginning and no end, a story that writes itself in a perfect, inescapable circle. It forces a haunting question. If you cannot change the past, were you ever truly free, or were you just following a script written with the ink of your own intentions? This is the cruel elegance of the predestination paradox, a trap where the hunter's footsteps are the very thing that herds the prey. The subtle drag of space-time is not just a theoretical curiosity, it is a phenomenon we can measure right here on Earth. Ring laser gyroscopes, incredibly precise instruments, have confirmed the lens-thirring effect, the frame dragging caused by our own planet's rotation. These devices use beams of light traveling in opposite directions around a closed loop. In a perfectly stationary universe, the beams would complete their journeys in the same amount of time. But because the Earth spins, it ever so slightly drags the fabric of space-time around with it, like a gentle current in a cosmic sea. This tiny motion creates a minute but measurable difference in the travel time of the two light beams, proving that our planet's rotation is not just moving matter, but twisting the very stage upon which reality plays out. The effect is vanishingly small, a whisper in the machinery of the cosmos. Yet its detection is a profound validation of Einstein's vision, a clue that the geometry of time is malleable. Now amplify this concept to an almost unimaginable extreme. Picture a civilization with technology far beyond our own, constructing a ring not of laser light, but of some impossibly dense material, spinning at a significant fraction of light speed. This would not be a gentle whirlpool like Earth's, but a furious vortex in space-time. The frame dragging around such a structure would be immense, warping the paths of objects and light in its vicinity. In theory, if the rotation was powerful enough and the system sufficiently compact, these warped paths could curve back on themselves, forming closed time-like curves within the ring's immediate vicinity. An object, or even a person, passing through this intensely distorted region might find their personal timeline shifted relative to the outside world, or even looped back onto itself. The ring laser, a tool for navigation on our planet, becomes the blueprint for a machine that could navigate time itself. While building such a device remains a fantasy of physics, its principle is rooted in an effect we have already touched. The universe has shown us the first, faint step on a road that could one day lead to yesterday. Particles routinely perform the impossible, vanishing from one side of a wall and appearing on the other without ever crossing the space in between. This is quantum tunneling, a well-documented strangeness where the rules of the everyday world break down. A subatomic particle, like an electron, faces a barrier it classically shouldn't have the energy to surmount. Instead of bouncing off, its quantum wave function allows it a finite, calculable chance to simply be on the other side, as if it took a secret shortcut through the mountain instead of climbing over it. Now, a handful of theorists have asked a breathtaking question. If a particle can tunnel through a barrier in space, could it, under the right conditions, tunnel through a barrier in time? This speculative idea proposes that a particle could have a small but non-zero probability of appearing not just in a different location but in its own past. It would not travel along a continuous path through the years, but would essentially make a discontinuous leap, vanishing from the present and instantly materializing at an earlier moment. Imagine rolling a ball towards a small hill it lacks the energy to climb. In our world, it rolls back. In the quantum world, it has a tiny chance to suddenly be on the far side of the hill. In this temporal version, the ball would have a tiny chance to suddenly be where it was 5 minutes ago. The implications are staggering, suggesting a form of time travel that is not a journey, but a spontaneous, probabilistic hop. Why is this theory relegated to the fringes of physics? The challenges are profound. First, quantum tunneling is inherently random and probabilistic. You could set up 1,000,000 identical experiments and only in a handful would the particle tunnel. For a time-tunneling event, this means you could never guarantee a journey or send a coherent message. You might set up an apparatus hoping to send a single electron to yesterday, but you could never control when or even if it would arrive. The second and far greater hurdle is causality. A particle tunneling to its own past could create the same paradoxes that plague other time travel theories. What if that past particle interacts with its former self in a way that prevents the very experiment that sent it back? The universe's rigorous enforcement of cause and effect seems to have no room for such random, acausal leaps. While the mathematics of quantum mechanics is famously bizarre, it has so far refused to yield a clear path for such temporal tunneling without violating its own core principles. This idea remains a ghost in the machine, a tantalizing hint that the quantum weirdness governing the very small might one day reveal a new understanding of time itself, where the past is not a distant country, but just another potential location waiting for a random, improbable arrival. Our reality might be a magnificent illusion, a three-dimensional image projected from a distant, two-dimensional screen. This is the holographic principle, a radical idea born from the clash between general relativity and quantum mechanics. It suggests that all the information describing everything within our universe, every star, every person, every moment in time, is actually encoded on a vast, cold boundary that surrounds us like the data etched onto a Blu-ray disc. The world we see and feel in 3 dimensions is just a breathtakingly detailed projection from that flat surface. If this is true, then time itself may not be a fundamental part of reality. The flow from past to present to future could be an emergent property, a side effect of how this cosmic projector reads and displays the information stored on its 2-dimensional source. This leads to a staggering possibility. If you could learn to rewrite the information on that boundary, you would not just be altering the present, you would be editing the past. It would be a form of time travel more profound than any machine, a manipulation of the source code of history itself. You would not be a traveler walking through time, but a programmer rewriting the timeline from the outside. The catch, of course, is that this remains one of the most abstract frontiers of theoretical physics. It is a speculative application of string theory and our quest for a theory of quantum gravity, a framework that remains just beyond our grasp. The energy and technology required to interact with the cosmic projector are unimaginable, perhaps forever placing this power beyond the reach of any civilization. Yet the principle stands as a profound clue. hinting that the key to time may not lie in building a better engine, but in learning to read the universe's original script. If a black hole is a cosmic drain from which nothing returns, then a white hole is its perfect opposite, a hypothetical fountain gushing matter and energy into the universe. It is the time-reversed twin of a black hole, an exit door where an entrance once stood. The mathematics of general relativity, in its beautiful symmetry, allows for this solution just as easily as it describes its dark sibling. Where a black hole's event horizon is a point of no return, a white hole's boundary would be a point of no entrance. Nothing from the outside could ever cross in, while everything from within would be violently expelled. Now thread these two opposites together with a wormhole, an Einstein-Rosen bridge, and you have a potential tunnel through space-time itself. One end is the black hole, the relentless absorber. The other end is the white hole, the eternal emitter. But if the two ends are connected, where and when does the white hole reside? Some models suggest it could exist in a different part of our universe, or even in a separate universe altogether. More intriguingly, it might exist at a different time. The matter falling into the black hole in our present could be the very same matter being vomited out by the white hole in the distant past, or perhaps in the far future, creating a stable cosmic circuit. This offers a vision of time travel not by moving a ship, but by rerouting matter itself through a natural cosmic plumbing system. You would enter the black hole and, in theory, be transmitted through the wormhole to emerge from the white hole in another time. Yet for all its mathematical elegance, most physicists consider white holes to be fantastically unlikely in our reality. The primary reason is the second law of thermodynamics, the universal rule of disorder. Our universe consistently moves from a state of order to chaos. A white hole, appearing spontaneously and spewing out ordered energy, would seem to violate this fundamental arrow of time. It would be like a shattered glass spontaneously reassembling itself and leaping back onto the table. Furthermore, no astronomical object matching the description of a white hole has ever been observed. The cosmos is full of violent explosions and energetic outbursts, but none that fit the precise, one-way nature of a theoretical white hole. They remain captivating ghosts in the equations, a testament to the sheer power of Einstein's theory to imagine realities far stranger than our own. If these cosmic fountains are forever closed to us, where else might we look for a bridge across the ages? Einstein's general relativity paints a picture of space-time curved by mass and energy. But what if that fabric could also twist? The Einstein-Cartan theory proposes exactly that, introducing a new property called torsion. In this refined vision of reality, space-time is not just a flexible sheet that dips under weight, it is a medium that can also be wrenched into a subtle spiral. This torsion arises not from mass alone, but from the intrinsic spin of elementary particles. Every electron and quark is like a tiny, spinning top, and in this theory, their collective rotation imparts a minute twist to the very geometry of the cosmos. Under normal conditions, this effect is vanishingly small, utterly dwarfed by the curvature caused by gravity. But in regions of unimaginable density, where matter is packed together and spinning in unison, the combined torsion could become significant. This could warp spacetime in profoundly new ways, potentially tying it into the kind of loops that form closed time-like curves. Imagine a universe so densely filled with spinning matter that the fabric of reality itself develops a cosmic corkscrew shape. A traveler navigating this helical geometry might find a path that circles back to its own beginning. This is not a machine you could build, but a natural consequence of a more complete set of physical laws, a hidden feature of reality that emerges only under the most extreme circumstances. The Einstein-Cartan theory remains a minority view, as its predictions are nearly impossible to distinguish from standard general relativity in most of the universe we can observe. Yet it stands as a powerful reminder that our understanding of gravity may still be incomplete, and that the true keys to time might be found not just in how matter warps space, but in how its spin might tie time into a knot. If the universe is capable of such a subtle, intricate twist, what other hidden geometries are waiting to be discovered? Navigating the multiverse would be the ultimate form of time travel. The many worlds interpretation offers more than just a solution to paradoxes. It presents a cosmos of infinite possibility. Every choice you have ever made, from the trivial to the life-altering, created a new universe where the other option played out. This is not a hypothetical, but a direct implication of quantum mechanics for some physicists. In this view, time travel is not a journey backward along a single, rigid line. It is a lateral move, a hop from one branching reality to another. An advanced civilization would not build a machine to visit 1969. They would build a vessel to navigate the infinite spectrum of 1969s that actually exist. You could step into a device and emerge in a past where the dinosaurs never went extinct, or where a different inventor created the light bulb, or where you yourself made a different crucial decision last Tuesday. This is how you truly sidestep every paradox. You are not changing your own history. You are simply visiting a history where things happened differently, a universe that was always there, waiting in the vast ensemble of all possible realities. Your original timeline remains pristine and untouched. This transforms the time traveler from a historical vandal into a pure explorer. The challenge would not be avoiding contradiction, but charting the infinite. How would you even map such a cosmos? How would you find your way back to a universe almost, but not quite, exactly like your own? The destination would not be a date, but a coordinate in a branching tree of reality, so vast it defies human comprehension. If every possibility is real, then every past you can imagine is already out there, a ghost universe waiting for a visitor. The relentless search for cosmic gateways and quantum tunnels might be looking in the wrong place entirely. What if the true vehicle for time travel has been with us all along, housed within our own minds? This theory pivots from the physics of the universe to the philosophy of perception, proposing that time is not a fundamental river flowing around us, but a construct woven by our consciousness. We do not passively experience time, we actively create it, stitching together a coherent narrative from a cascade of sensory inputs. Our brain takes the raw data of the present, compares it to memories of the past, and projects expectations for the future, crafting the steady, linear flow we all take for granted. But this perception is fragile, and under the right conditions, it can bend, stretch, or even shatter. Deep meditative states can produce a profound sense of timelessness, where minutes feel like hours and the constant mental chatter about past regrets and future anxieties simply falls away. In this state, some practitioners report a feeling of accessing a vast, eternal now, a perspective not unlike the block universe where all moments exist simultaneously. They are not physically moving through time, but their conscious awareness is shifting its focus within the infinite present. Similarly, certain psychoactive substances can dramatically warp this internal clock. A person under their influence might experience a lifetime of memories flooding back in what is objectively only a few seconds, or feel as though they are reliving a past event with perfect immersive clarity. These are not mere hallucinations in the traditional sense, but radical alterations in the brain's timekeeping machinery. The internal narrative that usually flows in one direction suddenly loops, stutters, or expands. If our standard consciousness is like a laser reading a DVD one frame at a time, these altered states are like the laser glitching, jumping to a different scene, or illuminating the entire disk at once in a blinding flash of insight. Advanced technology could one day refine this glitch into a tool. Imagine a neural interface that doesn't just read brain signals, but can directly manipulate the processes that create our sense of chronological order. Such a device could, in theory, allow you to subjectively re-experience any memory with the full force of original sensation, not as a faded recollection, but as a vivid reliving. It could potentially even stitch together new sequences, allowing you to feel as though you're walking through a past you never had, or sampling a future built from your own hopes and fears. This would be a deeply personal form of time travel, entirely confined to the theater of your own mind. You could not change the external, objective past, but you could fundamentally alter your relationship to it, healing old wounds or gaining new understanding. This theory reframes the entire quest. The destination is not a different year, but a different state of awareness. The machine is not made of metal and exotic matter, but of neurons and perception. If time is truly a story the brain tells itself, then perhaps the ultimate time machine is simply the key to editing that story. What if you could stop time not by traveling through it, but by watching it too closely? This brings us to the quantum Zeno effect, a bizarre phenomenon where observation itself seems to freeze reality. In the quantum realm, an unstable particle, like a radioactive atom, has a certain probability of decaying at any given moment. But if you continuously measure it, checking its state again and again in rapid succession, something strange happens. The act of observation repeatedly resets the particle's quantum wave function, effectively preventing it from decaying. It is as if a watched pot never boils, but on a fundamental, subatomic level. The particle remains stuck in its initial state, held in place by the relentless gaze of measurement. Now extrapolate this chilling idea to the flow of time itself. Time, after all, is marked by change, the movement of particles, the ticking of a clock. If continuous observation can prevent a single atom from changing, could a sufficiently intense and constant monitoring of a larger system halt its progression through time? This is the speculative leap. The theory suggests that by creating a field of perfect, uninterrupted quantum observation, you might be able to lock a region of space in a single, unchanging moment. A bubble of stasis would form where inside every atom is frozen, every process paused, and time itself stands still. Imagine a safe room where priceless artifacts are preserved not by controlling the temperature, but by suspending time within the walls. A person caught in such a field would not age, not breathe, not think, completely unaware that millennia are passing just outside the invisible barrier. The engineering required for this is, of course, beyond any technology we can conceive. You would need a method to observe every single particle within a volume simultaneously and continuously, a feat that seems to defy both practicality and energy constraints. Yet the principle offers a hauntingly different vision of time control. It is not about building an engine to move through the years, but about constructing a prison of perpetual now, where the relentless present is enforced by the ultimate surveillance. Could the very act of seeing the universe ultimately be what holds it in place? Beneath the quiet emptiness of space lies a seething, invisible ocean of energy. The quantum vacuum is not truly empty, but a turbulent sea of virtual particles that flicker in and out of existence in a relentless dance dictated by the uncertainty principle. These particle-antiparticle pairs borrow energy from the universe for an impossibly brief moment before annihilating each other, returning the energy loan almost instantly. This endless cycle of creation and destruction fills every cubic centimeter of the cosmos with a staggering amount of latent power, a background hum of reality that physicists call zero-point energy. If we could somehow tap into this fundamental energy source, the possibilities would transcend anything we currently consider possible. The power contained in the vacuum energy within a single coffee mug could theoretically boil all the oceans on Earth. This is not a conventional fuel, but the very substrate from which spacetime itself is woven. The theory of vacuum energy manipulation suggests that by learning to control this seething quantum foam, we could directly engineer the geometry of the universe. We could tighten or loosen the fabric of spacetime itself. Imagine creating a localized region where the vacuum energy is artificially suppressed. According to general relativity, energy and mass are equivalent, so reducing this energy would effectively create a region of negative mass, generating a repulsive form of gravity. This is precisely the kind of exotic matter required to stabilize a wormhole's throat or power an Alcubierre warp bubble. You would not be pushing a ship through space with rockets, but using vacuum energy to contract spacetime ahead of you and expand it behind you, riding a wave of manipulated nothingness. The time dilation effects within such a bubble would be profound. A journey that felt like a few hours for the crew could span centuries in the outside world, propelling them into the future. More exotic still, by creating specific, resonant patterns in the vacuum field, one might theoretically induce spacetime to fold into a closed time-like curve, a loop where the end of a journey connects to its own beginning. The challenge, of course, is beyond monumental. The vacuum energy is locked away by the very laws of quantum mechanics, its effects normally cancelling out to zero. Harnessing it is like trying to capture a specific wave in a storm-tossed ocean while ignoring all the others. The energy scales involved are so immense that any practical apparatus would need to operate on a level of precision we can scarcely imagine, perhaps using fields or structures built from spacetime itself to corral this raw, fundamental power. Yet, if such a technology were ever realized, it would transform us from passengers on the river of time into its engineers. We would not just be reading the cosmic code, we would be rewriting it. So if the very emptiness of space holds this incredible potential, what other hidden forces are waiting to be unleashed? The grandfather paradox is the ultimate puzzle of time travel, a question that has echoed through every theory we have explored. A man journeys to the past and confronts his own grandfather before his parents are conceived. He raises the weapon poised to erase his own existence. But what happens next depends entirely on which set of cosmic rules you believe are in play. This single, chilling scenario becomes a brilliant lens through which to view all the others. If the Novikov self-consistency principle governs reality, the trigger will never be pulled. A sudden noise, a slipped finger, a last-second surge of conscience, some event will always intervene. The universe acts as a master editor, ensuring the timeline remains a single, unchangeable story where the traveler was always a spectator, never an author. Their free will is an illusion, their actions merely fulfilling a past that already included them. Now, consider the same scene through the kaleidoscope of the many worlds interpretation. The gun fires, the grandfather falls, but this act does not erase the traveler. Instead, it instantly spawns a new, parallel universe, a branch where he was never born. The traveler watches as this new timeline unfolds, but his own original history remains perfectly intact, safe in its own cosmic thread. He has not changed the past, he has merely chosen a different one to visit, forever exiled from the future he knew. Then there is Stephen Hawking's chronology protection conjecture, which acts as the universe's bouncer. The moment the traveler even attempts to create this paradox, the cosmos retaliates. Perhaps the time machine itself explodes in a flash of quantum fury. Maybe a wall of impossible energy materializes to block the path. The paradox is not resolved logically, it is prevented physically. The universe violently defends the sanctity of cause and effect, making the contradictory act an impossible feat of engineering. Even the block universe theory has its own serene answer. In that eternal four-dimensional block, the traveler was always part of that past scene. Perhaps he was the mysterious stranger who startled his grandfather, inadvertently causing the very meeting that led to his own birth. His journey did not change anything because his presence there was always a fixed coordinate in the vast tapestry of spacetime. The grandfather paradox forces every theory to show its cards. Is our timeline a single, immutable thread, a fragile narrative we must protect, or just one strand in an infinite rope of possibilities? Does the universe care about our logic, or does it enforce its own with physical laws? This one simple question about a man and his grandfather reveals that the greatest mystery of time travel is not the how, but the what happens after. A civilization that has harnessed the energy of entire galaxies would view reality through a lens we can scarcely comprehend. Such a culture, a Type 3 on the Kardashev scale, would possess technology that seems indistinguishable from magic to us. For them, time travel might not be a theoretical puzzle, but a mastered discipline, as routine as our use of electricity. They could be using black holes as natural accelerators, calibrating the spin of a Kerr singularity to open a doorway to any era they wish to observe. They might have learned to harvest cosmic strings, those primordial threads from the universe's birth, weaving them into stable networks of closed time-like curves that span the cosmos. Their methods would be as far beyond our understanding as a smartphone is to a Stone Age tool. This leads to a haunting and inevitable question. If such beings exist, where are they? Why have we never encountered a single tourist from the future? The answer might be that they are all around us, but operating under a strict code of non-intervention. They could be like anthropologists studying a protected tribe, careful to leave no trace of their presence, ensuring our development remains purely our own. Their vessels might not be metallic ships, but constructs of spacetime itself, completely undetectable to our senses. Or perhaps their travel does not involve physical bodies at all. A truly advanced civilization might have transcended biological form, existing as pure consciousness or information, traveling back in time simply to upload their awareness into the planetary data stream of a younger Earth, experiencing our history as a seamless virtual recording. We would never see a machine materialize in a blaze of light. We would only notice, perhaps, a strange pattern in the static of the cosmic microwave background, a signature of their silent observation. The silence of the past is not proof that time travel is impossible. It may only be evidence that those who have mastered it are infinitely careful and infinitely wise. Our journey through cosmic strings and quantum foam brings us to a final, deeply personal frontier. After exploring 30 theories of physics, we must now confront the philosophy of time itself. If a working time machine stood before you, its implications would reach far beyond science, striking at the very core of your existence. The first and most unsettling question is one of identity. If you journeyed to the past and altered a single pivotal event, the person who returned would not be the same person who left. Your memories, your personality, even your physical body would be the product of a new and different chain of causes. Are you still you if your history is rewritten? This challenges the notion that we are stable beings, suggesting instead that our identity is a story we tell ourselves, a narrative fragile enough to be undone by a single changed detail. This leads directly to the ancient debate between free will and destiny. Is our timeline a dynamic, unfolding story where our choices genuinely matter, or is it a static, pre-recorded film where we only experience the illusion of choice? If the past is changeable, then our free will has terrifying power, granting us the authority to erase and remake reality itself. But if the past is fixed, as in the block universe or Novikov's principle, then our sense of agency is a beautiful, heartbreaking mirage. We feel we are writing our lives, but we are only reading from a script completed long ago. These models of time offer profoundly different answers. The dynamic theory, which sees time as a flowing river, makes time travel seem like an act of divine creation or destruction, a dangerous rewrite of a story in progress. The static theory, the block universe, makes time travel a simple form of navigation through a museum of frozen moments, where you can look but you cannot touch because your presence was always part of the exhibit. Stepping away from the machine, we are left with a quiet, lingering thought. The greatest mystery of time travel may not be whether we can build the device, but whether we are prepared for the answers it would force upon us. What does it mean to be a self if that self can be so easily unmade? Is our cherished free will nothing more than a passenger's belief that they are steering the ship? Perhaps the ultimate value of these theories is not in their promise of yesterday, but in the light they shine on the profound puzzle of our own existence here and now. We have ventured from the spinning heart of black holes to the quiet hum of the quantum vacuum, tracing 30 paths through the enigma of time. Each theory, from Einstein's relativity to the holographic principle, offers a unique key to a lock we have not yet opened. While a working time machine remains a dream of science fiction, this journey is far from a fantasy. It is a testament to human curiosity, a relentless push against the boundaries of what we think we know. These ideas force us to question the very fabric of reality, from the certainty of cause and effect to the nature of our own consciousness. They remind us that the universe is far stranger and more wonderful than it appears. The conversation does not end here. We want to hear which of these theories captured your imagination the most. Was it the cosmic escape hatch of a wormhole or the infinite branches of the many worlds? What time travel paradox keeps you up at night, pondering the nature of your own existence? Share your thoughts in the comments below, and if you are eager for more journeys to the edge of understanding, be sure to subscribe for our next deep dive into the mysteries of space and time.